lesson is about torque. Torque can be thought of as a twisting force, and the results you get from applying a force about a fulcrum is you can either twist something clockwise or counterclockwise when you apply a force at a lever arm distance. That's what torque is. It's a force applied at a lever arm distance. In the case of a seesaw, we've got an example here of two weights that are equally of the same mass and equally spread apart from the fulcrum on either side. So we should have a certain amount of torque in the clockwise direction equivalent to the same amount of torque in the counterclockwise direction. So when we run the simulation, there's no net torque, so there's no net twisting action of our teeter-totter. However, if we decide to move one of the masses to a different radius of, let's take a look at r equals to 3 now instead of where in this case it was 2. So now with a greater lever arm distance, we should have more torque and thus more twisting action. So the winner is our counterclockwise torque in this case, and so the system will rotate counterclockwise. Let's look at another example. Here's another balanced system, and since it's balanced, that means all of the torques counterclockwise and clockwise will add up to 0. So if you're ever given a system of many forces at many lever arm distances, you could find the net torque, kind of like that, of course, and that's the sum of all of your torques, so sum of all your r times f's. So let's count them up. I'm going to use red for counterclockwise, and we will add these up. We're going to say r is equal to 1 meter. That looks like 4. And so we have 4 times a certain amount of weight and 1 times a certain amount of weight. So it will be 4w plus 1w, giving us a net counterclockwise torque of 5w. Now let's compare that to clockwise. So we're going to try to go in this direction, and I'll use green for that. So how much torque do we have clockwise? Well, the sum of all of our clockwise torques, we're going to have one from this mass with force w at a distance of 2 meters, and we're going to have another one at a distance of 3 with the same amount of force of weight. So then we've got 2 times w plus 3 times w is going to make 5w. And notice that you've got the same amount of torque in both directions, therefore your net torque, counterclockwise minus clockwise, should be 0. And because it's 0, that's why we don't have a winner, and that's why we run the simulation and neither side wins. Now, if I were to take one of these and move it, let's take this one, move it over. I bet you can guess which side wins. See if you're correct. And let's pretend we wanted to counterbalance that by moving a different ball over. Remember, we just took one of these counterclockwise forces and changed its radius over by 1 in the left direction. So we gained counterclockwise torque by a unit of 1w. So all we have to do is take either one of these and move it over 1, and that should balance our system again, and it does.